Hello, everyone. Thank you so much for joining along to this GGS webinar. We've just got a couple of minutes and people will be joining. Today's webinar is led by Andrew, and we're going to be looking at atmospheric pressure and what are the worst case conditions for ground gas risk assessment. Do feel free to ask any questions you might have during, and we'll get to answering questions at the end. The webinar will last about an hour in total, and then we'll have around 10 minutes for questions. And I'll hand over to Andrew now. We can get started. Enjoy.
Thank you, Louis. Okay, so today's webinar is on atmospheric pressure and what can be considered worst case conditions for ground gas risk assessment. First, a very brief introduction to myself and GGS. You may already know that GGS has just recently celebrated 15 years trading and is recognised as a leading provider for continuous ground gas monitoring data, analysis, interpretation. I have now over 12 years experience as a professional environmental scientist at GGS, working in the investigation, measurement, management of hazardous ground gas substances. So, like Lewis said, please do ask questions which you can post at in the box at the bottom of your screen during the webinar. And I'll aim to answer those at the end. So the purpose of today's presentation is to introduce a simplified approach for when the assessment of atmospheric pressure is required for ground gas monitoring. It's taken a while to get to this point, and I'm delighted to be sharing the content of our technical white paper today, which will be published in a few weeks' time. The presentation will provide a brief summary to why atmospheric pressure is considered a critical part of the source pathway receptor contaminant linkage model in ground gas monitoring, and how this new simplified approach can provide a useful tool when the prediction of worst case conditions are needed in ground gas risk assessment. There'll be a few slides on how to define low and falling atmospheric pressure. I will then briefly discuss the variability of low and high pressure systems in the UK, as this will set the scene for the proposed simplified approach in assessing worst case conditions. I will then briefly discuss the methods used in the data analysis leading to the worst case thresholds, and the rates of falling atmospheric pressure most likely to influence ground gas behaviour and migration. The white paper is intended to be short and accessible, but it will also include a series of annexes which are for reference and for interest, but they'll also include additional information that can be used for the assessment of worst case conditions. I'll have time today to give you a flavour of what to expect in the annexes, such as the climatological summaries of different UK regions, a longer term analysis to the frequency of falling pressure, of rapid falling pressure and low pressure, and finally some case studies relevant to worst case and extreme conditions. So I'm just going to stop my video now and we can progress with the slides. Get going. So whilst an understanding of the relationship between atmospheric pressure and ground gas can form a critical part of the source pathway receptor linkage model, it is important to note that additional consideration should be made to all lines of evidence when establishing a robust gas conceptual site model. A clear understanding of the ground gas source, geological setting, groundwater behaviour and chemistry, and environmental variance can often be key in determining the risk from ground gas at the surface. There are many guidance documents to use that will support this development of a gas CSM in risk assessment. And our aim for the white paper and worst case thresholds is simply to provide an assessment tool for when atmospheric pressure is considered necessary as part of this process. And whilst it's recognised that not all sites require gas monitoring, and of course not all sites will require assessing with atmospheric pressure, atmospheric pressure is often a dominant driver of ground gas on many sites. This has long been recognised, and recording gas measurements with variable atmospheric pressure is written into guidance, which states that ground gas monitoring programs should capture time periods to when pressure is falling and low, as this will usually coincide when ground gas emission rates are at their highest. The rate of fall and the duration of fall are also key factors to consider. It is evident since the public inquiry to the LOSCO event in 1986, falling atmospheric pressure is recognised as a significant migration driver in ground gas contamination. And many guidance documents have since stated the importance of capturing a period of falling pressure and low pressure when undertaking ground gas monitoring. However, current guidance for what would potentially define worst case conditions in terms of falling atmospheric pressure is not available. There is no previous guidance that sets out a clear quantitative pressure fall threshold, or what would constitute worst case conditions with relevance to geographical areas or seasonality. Defining low and falling atmospheric pressure, guidance has also stated that ground gas monitoring should include a period when atmospheric pressure is below 1,000 millibars, and this has since been standard practice in the UK. However, when considering the site's geographical location or the time of the year the measurement was taken, atmospheric pressure regime below 1,000 millibars is not always an ideal indicator to low pressure. To clearly define when atmospheric pressure is low or high, it is first important to standardise the measurement to sea level. In the UK perspective, the standard mean sea level pressure is defined as 1,013.25 millibars, which provides a common value to compare atmospheric pressure across different locations and elevations. Also, it's worth noting that it's rare for sea level pressure in the UK to rise above 1,050 millibars or fall below 950 millibars. As average sea level pressure will vary each month and season, typical convention is to present sea level data into 5 distinct categories, which with very high pressure above 1,035 millibars to very low pressure below 990 millibars. For atmospheric pressure, a useful assessment tool is to record the 3-hour tendency or pressure trending. For weather forecasting in the UK, the Met Office records pressure tendency over a 3-hour period, whereby every hour the change in atmospheric pressure over the preceding 3 hours is noted as being either stable, rising, falling or slowly, or falling and rising very rapidly. This approach provides a clear numerical assessment to the rate of change in millibars and when pressure is falling rapidly or very rapidly. And this is easily captured and presented with time series data showing time periods when 3-hour tendencies exceeds 3.6 millibars and when pressure is rapidly falling. Often though, It will be the pressure trending or the rate of fall over the preceding hours and days that will influence the ground gas concentration and behaviour at the point of measurement. Historical time series data for weather and atmospheric pressure is available online, and a sequence of period monitoring visits can be further understood in the context of low and falling pressure in useful time series graphs. This simple step will provide a level of confidence to whether there is sufficient ground gas monitoring data in relation to the atmospheric pressure regime and whether falling pressure has been significant leading up to each event, to each visit. In this example, we can see weekly scheduled periodic monitoring visits, which are marked in red, and whilst low pressure, and a little here as well, and falling pressure have been captured, have visits coincided with potential worst case conditions. We can see that two visits coincide with the threshold for falling pressure, or a 3-hour tendency exceeding 1.6 millibars, but not rapid falling pressure, which does occur in the timeline. And here. This can be difficult to fully capture with periodic monitoring visits, and if atmospheric pressure is likely to be a key driving mechanism on the ground gas regime, then continuous ground gas monitoring should be considered to support the development of a robust gas conceptual site model. So a very brief meteorological summary. The UK's temperate maritime climate is influenced by westerly winds with anticyclones and depressions often blowing in from the Atlantic. With the transit and intensity of high and low pressure systems across the UK driven by the position of the jet stream, which in turn is influenced by the North Atlantic Oscillation, or the NAO. The common pressure features seen in the North Atlantic Ocean for large regions of relatively high pressure centred over the Azores and low pressure centred over Iceland. And the North Atlantic Oscillation describes the relative changes in pressure between these two regions. Strong winds and warm air from the west will be a dominant feature of a positive NAO phase, whilst a negative phase will often lead to a weakened jet stream and more frequent but lighter winds from the east and northeast. The NAO will have a strong influence on UK winter weather and weather patterns in general, affecting both short and long-term trends and regional or local pressure. The next few slides will introduce the simplified approach and what can be considered worst case conditions for falling atmospheric pressure. An historical data set will provide time reference to meteorological variance and allow for normal and extreme conditions to be understood, with the extent and significance of falling atmospheric pressure that has occurred in the past, providing a quantitative threshold for the prediction of worst case conditions, and when this is required in ground gas risk assessment. This is calculated by using the 95th and 90th percentiles to the rate of falling pressure in millibars per hour and from historical time series data. Whilst the 95th percentile will provide a clear understanding to an expected worst case pressure fall, it may also be appropriate to consider the 90th percentile as being relevant in some cases. The use of either threshold in ground gas risk assessment is supported by understanding all the lines of evidence and the gas conceptual site model, but also using professional judgment. So what did we do? The UK was split into 4 regional zones: the northwest, northeast, southeast and southwest. The 4 zones were considered appropriate to perform analysis on regional and seasonal variance in atmospheric pressure. Each zone was configured using Ordnance Survey UK national grid squares, with 7 locations selected in each zone, based on geographies and topography, with a simple aim to ensure a representative sample in each zone. They varied from Wick in the northeast to Truro in the southwest. Hourly sea level data was used from Open Meteor for all locations for a 6-year period from the 1st of January 2017 to 31st December 2022. And this period was considered appropriate to capture monthly seasonal atmospheric pressure variance and provide an appropriate representation to normal weather conditions, but also ensure that extreme events driven by regional climate were present in each data set. Every falling pressure event lasting at least 8 hours or more, with a minimum fall of 8 millibars, were selected from each data set, and analysis included the duration of each fall, the total fall in millibars, and the maximum 3-hour tendencies for each fall, and also the average rate of falling pressure in millibars per hour for each fall. The criteria for falling pressure was to filter out the shorter periods of falling pressure and ensure each data set focused on falls considered relevant to ground gas. To establish whether the rate of falling atmospheric pressure in your assessment exceeds worst case thresholds requires the average rate of fall over an 8-hour reference period to be calculated. The worst case pressure conditions are presented on this slide for the northwest region. The overall trend of worst case thresholds are similar in each region. Sorry, no, for all regions, not in the northwest. The overall trend for worst case thresholds are similar in each region, with a clear seasonal trend of a higher expected rate of fall during the winter months, December, January and February, and a lower expected rate of fall during the summer months in June, July and August. It may be relevant to complete assessment using monthly worst case conditions, or using regional annual averages, or even the UK annual average 95th percentile set at 1.11 millibars per hour. With comparison to annual and seasonal trending in all regions, it is evident that the rate of falling pressure is lower during April than perhaps anticipated. The atmospheric pressure regime in April could be anomalous when compared to longer term trends, with the worst case thresholds simply a measure of the atmospheric pressure regimes occurring between 2017 and 2022. Also, when compared to other regions, the northwest exhibits a sharp increase in worst case falls occurring in September. Whilst it may be evident that extreme falling pressure events tend to influence this region in early autumn, it could also be variance within the data used, and longer term trending could be more aligned to other regions or vice versa. However, averaged overall or used by location or by region, then the analysis provides a threshold to what worst case pressure conditions can be expected. The 90th percentiles are presented in the white paper, and whilst proportionally lower and show a similar trend over the year, the extreme observations in the northwest region are less pronounced. For comparison purposes today, the average annual 90th percentile for the UK over the year is 0.99 millibars per hour. Also, the first annex will present the 95th and the 90th percentiles for each month and for all 28 locations. I'm just having some water. This slide presents the data to show the frequency of falling pressure across each month. The frequency of falling pressure events is shown to be higher in the north, along with a strong seasonal signature, with expected frequency of approximately 8 falling pressure events during winter months compared to around 3 during the summer. And we can clearly see that in the northern regions, we can expect more falling pressure events more or less all year, except when they're aligned with summer regions during April and December. So we're now going on into the annexes, and this slide provides a summary of expected atmospheric pressure regimes for each region, which are presented in the annexes. I've just collated a few examples to provide you all with a flavour today. This slide provides an example of the Northwest region, and over the 6-year data set, the maximum atmospheric pressure recorded in the Northwest region was 1,050.4 millibars in Ullapool, which occurred on the 29th of October 2020. And the highest regional average pressure is also evident in March, with each location tending to record maximum readings within this month too, especially at locations with a higher latitude. In general, July is consistent in recording the lowest maximum pressures across each location. The lowest minimum pressure was also recorded in Ullapool at 949 millibars, which occurred on the 9th of February 2020. 2020 was quite remarkable that we had these two rare events just several weeks apart and at the same location. Overall, minimum pressures tend to be recorded in February, especially at locations with a higher latitude, as we would also anticipate December also tends to be a month when low atmospheric pressures are recorded across all locations. For each region, the annexes include a table and graphs for the average atmospheric pressures that can be expected for each month. For the Northwest region, in this table, the lowest average monthly atmospheric pressure also occurs in Ullapool in December, with all other locations recording their lowest averages during this month too. In general, all locations exhibit seasonal trending, with other winter months recording low atmospheric pressures, although January is higher than other winter months and than in autumn. All the highest atmospheric pressures were recorded in April, with a general trend of higher average pressures during the spring and summer. Both northern regions showed similar trend, which are lower each month than the southern regions, except for April. The southern regions also trend the same throughout the year and average higher in January and April. The lowest monthly averages are shown to occur in October, November and December in all regions. The average monthly pressures are low in February in both northern regions, an approximate 5 millibar difference between the southern regions. I referred to geographical differences in the last few slides, especially between the north and south. We can observe the linear relationship between latitude with the expected annual average atmospheric pressure and the frequency of falls in these two plots. And whilst there is likely to be local variance, atmospheric pressure in the north will tend to experience lower annual average pressures as locations are closer to the polar front and the Icelandic north, especially in the winter. Southern areas being closer influence the subtropical higher pressures tend to have slightly higher averages. The frequency of falling pressure events are also related to latitude, with a higher annual average frequency of fall in the north, as they are often closer to the position of the jet stream. In both cases, the linear relationship is quite strong. And whilst there's a similar trend, the linear relationship is not strong between latitude and the rate of fall in this plot. This is largely attributed to each site's longitudinal position and the dominant track of low pressure systems occurring across the UK, i.e. progressing in an easterly and northeasterly direction and having further influence on westerly locations. So a few slides on the probabilities of experiencing falling pressure. These calculations are based on the total amount of hours of rapid falling pressure that has been recorded within each time series data set. A probability score has been calculated in each month for when falling pressure can be expected to occur throughout the year, and here is summarised into each region. It is clear that very rapid falling pressure is more frequent in the winter months, with occurrences above 6 millibars over the preceding 3 hours, tending to be more frequent in the higher latitudes in the northern regions, whilst it is evident that winter months can potentially extend into spring and autumn in the north. Very rapid falling pressure is restricted to just the winter months, December, January and February in the southern regions. And the probability of rapid falls is more likely to occur in all seasons, but less likely during the summer months, with a higher probability in the north during spring and autumn when compared to the southern regions. And we can experience falling pressure, which is defined as 3-hour tendency at or above 1.6 millibars in every month and across all regions. So is the frequency in falling atmospheric pressure changing? Well, the scientific consensus that our climate is changing is clear. In the UK, we know this is already impacting our weather. Temperatures are rising, with more frequent severe heat waves and more intense rainfall becoming normal occurrence. The key changes in UK climate are expected, with likely to be differences between summer and winter weather, with more sustained extreme events becoming more frequent. Temperature, rain and wind impact us directly and rightly get a lot of attention in the context of climate change. But is atmospheric pressure changing? Is falling pressure becoming more frequent or less frequent? Are we experiencing more storms and an increase in more extreme falling pressure events? To provide an insight to these questions, a longer-term analysis of atmospheric pressure variance was completed at 7 sites from the 1st of January 1970 to 31st December 2023. The 7 sites were spread across the UK and included Southampton, St Ethan near Cardiff, Northup near London, Coleshill near Birmingham, Rosthern near Manchester, Newcastle, Glasgow. The analysis included the frequency of falling pressure events and the time distribution of rapid falling pressure and low or high pressure. In short, the 7 sites were spread across the UK and included Southampton, St Ethan near Cardiff, Northup near London, Coleshill near Birmingham, Rosthern near Manchester, Newcastle, Glasgow. The analysis included the frequency of falling pressure events and the time distribution of rapid falling pressure and low or high pressure. there is monthly, seasonal and geographical variance between the 7 locations. This graph shows the rolling hourly average of rapid falling pressure during December occurring in Glasgow. It also shows the deviation or anomaly from the normal average period, which is calculated between 1991 and 2020. And you can see the variation over time when compared to the climate normal period and the years of relative storminess. 1991, 2013 were standout years in Glasgow during December. From the rolling average, the hourly frequency of rapid falling pressure shows a clear increasing trend over time. And all this analysis is presented into tables for each location and month. This table provides Pearson correlation coefficients for the rolling averages for rapid falling pressure from 1980 to 2023 in all locations, which is calculated as monthly hours with a 3-hour tendency at or above 3.6 millibars, or rapid falling pressure. A negative correlation denotes that the number of monthly hours of rapid falling pressure is decreasing over time, whereas a positive correlation denotes the hours of rapid falling pressure is increasing. In all tables, only linear relationships above 0.5 are considered. A negative or positive relationship above 0.75 is considered to be very good, which are shaded in the table. Months have also been grouped into relevant seasons. Here we can see a strong indication that rapid falling pressure is decreasing in autumn in all locations, and especially during the month of September, whilst rapid falling pressure is increasing in all locations during December. And possibly in the north during winter months, here in Newcastle and Glasgow. Although there's no significant change in any location during January. We also looked at low pressure. Is low pressure occurring more frequently? And this has been measured by counting the monthly hours below 990 millibars, or very low pressure. Again, a negative correlation shows total monthly hours below 990 millibars is decreasing over time, and a positive shows correlation shows below 990 is increasing. There's a strong indication that the occurrence of very low pressure is increasing during autumn, and especially in November in all locations. Overall, very low pressure appears to be decreasing in the south but increasing in the north. However, the trend is not significant. Are we experiencing very high pressure more often? Is it increasing or decreasing? And this has been measured by counting monthly hours above 1,035 millibars, or very high pressure. And again, a negative correlation shows that that's decreasing over time, where a positive correlation denotes hours above 1,035 are increasing. And the frequency of very high pressure is shown to be increasing in all locations during March, June and December, and shows a marked upward change when analysed across the entire year. Although some months that don't show any change, there is a clear increasing trend across the UK in all seasons except autumn, which is just restricted to a few southern locations and not the two most northern locations. What about average atmospheric pressure? Well, this table shows average monthly pressure and how it's changed since 1970. A negative, again, correlation shows that average pressure is decreasing over time, and a positive correlation shows that its average pressure is increasing. Whilst it's quite a complex picture, atmospheric pressure is shown to be changing over time, with both regional and seasonal differences evident. When we consider the ideal gas law, the formation of low and high pressures being directly related to air temperature and humidity, with warm, humid air being less dense, leading to lower pressure, while cold, dry air will increase air pressure due to its higher density. This may begin to explain the decreasing trend in average pressure during the summer, which is apparent in all locations, and possibly a measure of atmospheric pressure in summer becoming more increasingly warmer and wetter. To determine longer-term trends in the frequency of falling pressure events, the rolling monthly average has been calculated for all the pressure falls occurring in Glasgow from 1970 to 2023. This graph shows the monthly falling pressure events of at least 8 millibars lasting 8 hours or more, and the monthly data sets are grouped into seasonal rolling averages from 1980. The monthly data sets are, the frequency of falling pressure is increasing in all seasons, and this is evident when the overall average is compared to the climate normal average, which is a 30-year period between 91 and 2020. There is a strong linear relationship in both winter and summer, showing increasing trend overall, but only a moderate relationship in spring and autumn, when the overall increase is slight. So now on to the case studies. The first case study provides an example of an extreme falling pressure event associated with Storm Kieran on the 1st and 2nd November 2023. Whilst the worst impacts of the storm in terms of wind and rain occurred across northern France and the Channel Islands, the lows in atmospheric pressure were quite exceptional for the south coast of England, and especially for the time of year. This graph shows the track of falling pressure across the south coast of England from Falmouth in the west to Eastbourne in the east. And the locations in between are Plymouth, Exeter, Weymouth, Bournemouth, Southampton, and Portsmouth. A minimum atmospheric pressure was recorded in Weymouth at 952.8 millibars at 5 AM on the 2nd of November, and a low pressure of 953.1 millibars recorded shortly after at 6 AM in Southampton. This is the lowest recorded atmospheric pressure in November in Southampton from the analysis of monthly minimum atmospheric pressures between 1970 and 2023. During the same period, only one lower monthly pressure in Southampton has been recorded, which was 951.1 millibars recorded on the 25th of February 1989. So the atmospheric pressures associated with Storm Kieran were exceptionally low for the south of England, and especially for the time of year. And we can see the low pressures recorded at each location, and the point at the centre of the depression when it reached landfall, with higher low pressures recorded when the storm was further out to sea, and when the centre of the depression was tracking further inland. When we look at the lowest reading recorded eastbourne. And you can see the development of Storm Ciarán as it began to approach the UK, tracking towards the south coast. And the rate of falling pressure was also significant during Storm Ciarán, with a maximum 3-hour tendency of 14.1 millibars recorded in Plymouth and Exeter at 9 p.m. and 10 p.m. respectively on the 1st of November. And this is as the Storch approached from the west. As Storm Ciarán passed over the south coast, there were 10 consecutive hours of very rapid falling pressure. That is 3-hour tendency above 6 millibars, with the most significant fall of 38.5 millibars over 13 hours recorded at Falmouth, which included a fall of 25.5 millibars over 6 hours, and a maximum rate of fall averaged over 8 hours at 4.1 millibars per hour. Since 2015, it's been convention to name storms, which run in alphabetical order from the 1st of September to the end of August. The 2023-24 season contributed to 12 named storms, and this is the highest number of storms in a single season since Norman's naming storms began. This case study summarises atmospheric pressures associated with the last named storm of that season, Storm Lillian, which occurred just a few weeks ago between 21st of August and 23rd of August. Analysis has been completed of the atmospheric pressure regimes for all the 28 locations used to provide thresholds for worst case conditions, and included the minimum atmospheric pressures and the maximum rate of falls recorded during Storm Lillian. This table provides a summary of the analysis of 8 of the 28 sites included, with latitude, the minimum pressures recorded, the maximum falls, in both the 3-hour tendencies and the 8-hour averaged. And the table also provides the worst case thresholds for August. And the column F provides a difference between the two, and a positive number indicating when falling pressure exceeded worst case conditions for August. The lowest atmospheric pressures and the highest rate of falls were recorded in Carlisle and Newcastle. And we can see this relates to the yellow warnings issued for wind and rain and the anticipated track of the storm across the UK. The lowest pressure of 981.7 millibars was recorded at Newcastle, which is considered very low, and especially for August. The average August minimum atmospheric pressure recorded at Newcastle between 1970 and 2023 is 994.7 millibars, which is, and with only one reference to a lower pressure of 975.8 millibars recorded in August, which was in 1992. Out of the 28 locations, 22 of those exceeded the 95th percentile for August, confirming worst case conditions occurred for the time of year. In fact, 20 of those locations still exceeded the annual average for worst case thresholds, measured at 1.11 millibars per hour over the 8-hour reference period. With reference to probability scores presented a few slides ago, it is unusual for rapid falling pressure to occur at this time of year. And from the 28 locations, only 4 did not record a rapid falling pressure, and all these were located in the southeast. The maximum rate of fall was also recorded in Newcastle, which was at 8.7 millibars over the preceding 3 hours. And since 1970, very rapid fall in pressure has only been recorded in Newcastle on 6 separate occasions during August. And this was in 1970, 73, 79, 85, 92, and 2020. And during these other events, a maximum 3-hour tendency of 8.5 millibars was recorded in 1985, which would make the rate of fall in pressure in Newcastle during Storm Lillian a new record for August. And now, almost returning full circle to the final case study, the importance of atmospheric pressure in driving ground gas migration followed the LOSCO inquiry, and has been reiterated in multiple guidance documents since. The inquiry determined that falling pressure was a key driver in landfill gas migration that led to accumulation of ground gas in the void below 51 Clark Avenue, and the subsequent an accumulation of ground, and subsequent explosion at approximately 6:30 a.m. when the heating system was switched on. Although there was no fatalities, the 3 occupants inside were injured and the house was destroyed. We know from the inquiry that the rate of falling pressure was a significant factor and noted to include a fall of 29 millibars over 7 hours, with an average fall of 4 millibars per hour leading up to the incident. And the atmospheric pressure regime, the rate of fall, 3-hour tendency either side of the 24th of March is plotted on this graph, and we can see the time series. In the time series graph, the rate of fall peaked at around 6 a.m. just before the explosion, whilst falling pressure continued to fall until 11 a.m. and reached a low of 958.4 millibars. In total, there was 10 consecutive hours of falling of rapid falling pressure, but out of these, 5 of these hours were recorded after the explosion. And we can see the rate of change in pressure leading up to the explosion with the maximum rate of fall recorded at 6 a.m. at 14.3 millibars over the previous 3 hours. When compared to worst case threshold for March, the falling pressure is shown to exceed this rate, 1.27 from around 2 a.m. in the morning. The rate of fall associated with the LOSCO event is quite extreme, with consideration of the maximum rate of falls averaged over the 8-hour period, and from analysis completed between 2017 and 2022. The maximum rates of fall average over an 8-hour period are presented here for all 28 locations used for the white paper, with the highest rate of 3.5 millibars per hour recorded Southampton on the 10th of December 2017. We can see other locations impacted by the same storm in the South East region. And the next most significant fall in pressure event impacted the Far North region on the 30th of January 2022, with the highest rate of fall calculated at 3.44 millibars at Hullapool. Yet we have seen a greater rate of fall over the 8-hour period during Storm Kieran at 4.1 millibars per hour recorded at Falmouth, which was on par with the fall in pressure experienced during the LOSCO event in March 1986. This is all highlighted to make reference that rapid fall in atmospheric pressure, including extreme events, can impact anywhere across the UK. And whilst the most extreme events are most likely to occur during the winter, With the example, Storm Lillian and Storm Kieran, significant events can occur at any time of the year. And what this analysis provides is clarity to what can be reasonably expected across all regions and during each month, with the rate of thresholds that can be used to assess worst case atmospheric pressure conditions, and this is relevant to your ground gas risk assessment. So that wraps up the slides for this webinar. Thanks for listening, and look out for updates over the next few weeks for when the white paper will be released. Just trying to switch on my video back on, and just to remind you, we have 2 more free webinars this year, which you can sign up for these if you haven't already on our website. And we still have 2 A to Z ground gas training events this year. The next one being in London next week. And these provide an opportunity for face-to-face training. Again, more information can be found on our website. But thanks for listening. I hope you lasted this long and found the presentation useful. If you've posted any questions, I can aim to answer those now. So we've got a question asking whether Belfast data had been given any consideration or inclusion in the study. It wasn't included in the Northwest region, but it was considered Northern Ireland would be relevant to that region as well. It was just really focused on a UK context, so didn't include Belfast for that reason. The 1987 hurricane event, yeah, it's been given some consideration. I did look at that as a case study, not presented it here today. It wasn't as extreme in terms of pressure in some of the examples provided today. It was more extreme, I think, for the wind and for the more significant for the the wind, but I can't remember the term now, but it was the first time it got introduced into meteorology and has been quite a focus for research since. So it was quite significant for that reason, but not for what I've seen in pressure, but it has had some consideration.
Before you answer the next one, I can see a couple of people have raised their hands. There is a Q&A box at the bottom of the screen if you wanted to answer a question. And also someone did ask about the recording and if they can catch up as well. But for anyone else, after the webinar, we post the recordings on our YouTube channel and across social media and stuff. So keep a look out there if you wanted to. I'll let you get back to the other questions, Andrew.
Yeah, okay. Thanks, Louis. How do you think this will affect monitoring frequency for spot monitoring? Well, it's about understanding the gas regime during those events and the gas regime, the atmospheric pressure leading up to the monitoring visits. It's often the behaviour of atmospheric pressure over the preceding hours and days that can have influence on gas concentration and behaviour. And it's important and useful to understand how the atmospheric pressure has trended during those each and every visit. It's about capturing variability and whether you have significant confidence level in your results when assessing to atmospheric pressure. That's the key. You need to continue measurements until the point where no more measurements are going to affect the risk assessment. The same question is also asked, how do you think worst case conditions can be better integrated into ground gas risk assessment? Again, it's partly based on professional judgment, but those monthly, regional, annual, and each location worst case thresholds are all relevant. Whether you use them in the assessment is based on that they're to assess to, and they can be used within the risk assessment, whether they're relevant. Were you sponsored to do this work? No, it's been largely completed in my own time, really. It set out to be quite a simple task, but those tasks are never as simple, are they? So it did take up quite a bit of time, and it's been ongoing for quite a well, its inception probably a couple of years ago to this point now. Over the last couple of weeks, I have focused on finishing the white paper, which is should be ready to. It's almost there to issue in a few weeks' time. Ben has asked, noting lower opportunities to conduct targeting sample. So I think Ben's on about attending site for periodic monitoring. You know, it's a good point in terms of worst case falling pressure. What's a useful function on historical time series online data? And I provided a couple of examples of where they're available. They're available freely online, but you get more features when you pay for them commercially. You can also use the forecasting functionality of that data, and they're quite useful in predicting, certainly for the next 7 days, when you're going to experience falling pressure, when that falling pressure is expected to be rapid falling pressure. So you can time visits accordingly. In reality, that is always a challenge in my experience, and continuous monitoring obviously has some benefit with capturing all those events with further clarity, but also understanding how the gas regimes responded, not only during falling pressure, but rising pressure, and whether worst case conditions have been captured is much easier to obviously capture with continuous monitoring. So it's not a cheeky question at all. The white paper is going to be free and be available to, I think, download from our website initially. I think that's going to be the forum where it will be available. Got another question. Dissolved gases such as methane and changes in atmospheric pressure, it's noted it doesn't tend to get picked up notable concentration during monitoring, except when there's a rapid fall in pressure. We see dissolved gases impacting on the gas regime and what are measured in the well quite often. It's usually quite sometimes subtle pressure differences that instigate that degassing and ground gases collecting in standpipes. I think that's it for questions. Sorry, there's one here. Are there any locations which are disproportionately affected by atmospheric pressure changes? Well, the northwest regions or northern regions in general are experience you'll see that in the differences in worst case conditions. Further north, it is related to latitude. You are likely to experience greater falls in pressure with higher latitudes, but also this is influenced by the position and tracks of the jet stream and where they occur in the UK. We often, western regions being more proportionately affected. I think that wraps up for questions today. Appreciate you all logging in to listen. If you do feel that you've got some questions that haven't been answered, please send me an email. I'll be happy to reply and answer those if I can.
Thank you so much, everyone, for joining. And like Andrew said about the white paper, if you follow us on LinkedIn or sign up to our mailing list, you'll get news about it being distributed there. Yeah, wonderful webinar, Andrew, and thank you, everyone, for joining along today.
Thanks, Lewis.
Bye-bye.